Now, another way that exponential decay functions are used is for carbon dating. And carbon dating is looking at, again, just like we looked at previously with plutonium, is measuring the half-life of carbon 14. And it is used to often to determine or estimate the age of fossils and other material. Now, there's a lot of controversy. There is controversy, I should say, on carbon 14 dating. You won't hear it a lot uh, because carbon 14 dating has been used to verify, I guess, an old Earth concept, and so there's people that dispute that. In fact, I may include a video for those that have a dispute with carbon 14, just so that you'll know that it is not 100% accepted throughout the scientific community, although you'll be told that it is, like a lot of things that we're told. But carbon 14 is going to follow this same exponential decay model. Y equals A E, natural base. I think I said natural log a lot last time. It's natural base of negative K raised to the value of negative KT. Now, in one of the examples that was spelled out in the book, it calculated K for carbon 14, and that was K for carbon 14 is equal to 0.00012. Now, let's look at our problem here. A specimen that was originally contained 42 milligrams of carbon 14 now contains 8 milligrams. How old is the fossil? So we're going to be trying to solve for this T, time, in this case. But let's set up our equation. Now, if A is 42, that's what we were given, originally contained. A is the initial value. And we now have 8 milligrams. So we substitute that in for Y. So we got 8 equals 42 E raised to the power of negative 0, I'm putting in 0.00012 for K, and T is the variable we're going to solve for. Well, first I'm going to divide both sides of this equation by 42, and that's going to give me 8 over 42 equals E, again raised to the power of negative 0.00012 times T. And I could reduce this 842 at least to 421. I don't have to, but I think I will. And let's see, so now I'm going to take the natural log of both sides. So I'm going to say ln of 4 over 21. I'm going to reuse this reduced value, simplified value of 8 over 42 equals the natural log of base E raised to the power of negative 0.00012 times time. Well, this is going to let the natural log and the natural base cancel. And so now we've got ln 4 over 21 equals negative 0.00012 times time, and time is what we're trying to solve for. And so we're going to divide both sides by the negative K, and so then we have ln 4 over 21 divided by negative 0.00012 is going to approximately equal our time. And when we perform that calculation, enter this into our calculator, then we're going to get 13,000, and we're going to just round it to the nearest year, 819 years approximately is equal to the time. So we're estimating, based upon this model, and models sometimes are incorrect, that this fossil would be 13,819 years old. Now we're going to look at another one where we're going to we're going to solve for how much carbon-14 should be in the animal. Hold on. All right, so here we got a woolly mammoth specimen, and it was thought to be about 12,000 years old. And if that's the case, based upon this model, and again, I'm going to write it right here, y equals a natural base times negative k times t, and in the case of carbon-14, k equals 0.00012. How much carbon-14 should be in the animal? So we're going to solve for y. Now, what should we put in for a? Well, if a is represented in terms of percent, then 100% is where we start. And we can just say that a is equal to 1 times e raised to the power of negative k, which negative k is equal to 0.00012, and our time we're given is 12,000. And all we really got to do is just put in our calculator e raised to the power of negative 0.00012 times 12,000, and we'll find that y is equal to, and we're going to put it in a percentage and round it to the nearest tenth. I encourage you to put this in your calculator, and we're going to get 23.7%. Check it out. Check on your calculator. Very good.